Today we're going to be talking about finding slopes of tangent lines and areas in terms of polar coordinates. So you might be thinking that if I give you a polar equation, r equals f of theta, that you could find the slope of the tangent line by finding r prime equals f prime of theta. Unfortunately, that's not true. When we're looking for slopes of tangent lines, it matters what coordinate system we're in. A slope should always be change in y over change in x. We want the change in the vertical distance divided by the change in the horizontal distance to give us an actual slope here. So what do we need to do? Well, fortunately what we can do is we can actually rewrite a polar equation in a parametric form. So we know that when we're dealing with polar, we have x equals r cosine theta and y equals r sine theta. Well then, we can say that x equals f of theta cosine of theta and y equals f of theta sine theta. And now we have written our polar equation parametrically with a parameter of theta. Now we can use what we already know about finding the derivatives dy dx of parametric equations. We know, see the box above there, that the derivative dy dx is going to be dy d whatever your parameter is. So our parameter here is theta divided by dx, d whatever your parameter is. And so in our case, we're going to be looking at the derivative in terms of theta of f of theta sine of theta divided by the derivative in terms of theta of f of theta cosine of theta. And that's pretty easy to figure out. If we want to simplify this, we can use the product rule on top and bottom, and we get f prime of theta sine of theta plus f of theta cosine of theta divided by f prime of theta cosine of theta minus f of theta sine of theta. Now this last formula, it is kind of the easiest one to use, but it's really hard to remember. So it might actually be easier to remember this derivation up here, that it's just using the derivative of the parametric equation. And here's a summary of what we've just said. Notice though that we do have to be worried about angles theta naught for which f of theta naught is 0 and f prime of theta naught is not 0. What can we say about those? Because if we have f of theta being 0, then we would be able to simplify this a little. So we would have f prime of theta sine of theta, and then the f of theta is 0, so the rest of that goes away, divided by f prime of theta cosine of theta. And notice then the f primes also cancel out, and we're just looking at sine of theta over cosine of theta, which is tangent of theta. So we have a slope of tangent of theta, and we know then f of theta, our radius, is 0. This is in the case, again, where f of theta equals 0. We know that it goes through the origin, and so we know a point, and now we know the slope, and that's enough to determine our tangent line. Our tangent line turns out to always be the line of angle theta. So here they did it with theta naught, so it's probably easier to read. You get, for any angle theta naught where you're going through the origin, but the derivative is not 0, then the tangent line is exactly theta equals that constant theta naught, and it has slope tangent of theta naught. This problem asks us to find the horizontal and vertical tangent lines of the curve r equals 1 plus sine of theta. Here we have a picture of the curve, so we can kind of guess where these tangent lines should be. We expect there to be a vertical tangent line here and here, possibly here, it's hard to tell, and there should be a horizontal tangent line kind of there at the top and on each of these bubbles. So how do we actually figure this out? Well, we now have a formula for the tangent lines, dy dx, equal to f prime of theta sine of theta plus f of theta cosine of theta divided by f prime of theta cosine of theta minus f of theta sine of theta. And we know that then a tangent line will be horizontal if this is equal to 0, but a fraction is only equal to 0 when its top equals 0. So to get a horizontal tangent line, we're looking for the points where f prime of theta sine of theta plus f of theta cosine of theta equals 0. Similarly, to get a vertical tangent line, that's where the derivative is undefined and in such a way that the bottom of the fraction is equal to 0. So we're looking for places where f prime of theta cosine of theta minus f of theta sine of theta equals 0. All right, so for our particular function, we have f of theta equaling 1 plus sine of theta, and f prime of theta equaling cosine of theta. So first, if we're looking for horizontal tangent lines, we want to find the places where cosine of theta sine of theta plus 1 plus sine of theta cosine of theta is equal to 0. Note too that we want the bottom not to be 0, because then we would just have something undefined altogether. So we want something where the top equals 0 and the bottom does not equal 0. So let's see if we can figure this out algebraically. Well, we're looking at cosine of theta sine of theta plus cosine of theta plus sine of theta cosine of theta, which is going to be 2 cosine of theta sine of theta plus cosine of theta equals 0. Factoring out a cosine of theta, we get cosine of theta times 2 sine of theta plus 1. So we should get the points where cosine of theta equals 0, or the points where 2 sine of theta plus 1 equals 0, which would mean that sine of theta is negative 1/2. Cosine of theta is 0 when theta is equal to pi over 2 plus k pi. And sine of theta is equal to negative 1/2 when theta is equal to negative pi over 6 plus 2k pi, or when theta is equal to 7 pi over 6 plus 2k pi. So you can go back and look at your unit circle if you don't remember that off the top of your head. So does that make sense if we go up and look at our graph? So when theta is 1/2, well, that would be right here, right? That's theta is 1/2. And then we have negative pi over 6. So here's 0. If we go negative pi over 6, it should be somewhere around here. So yeah, that makes sense. And then 7 pi over 6, that's just past pi. So it should be somewhere over here. And yeah, that makes sense. So those are all of our horizontal places where we have horizontal tangent lines. Now let's see if we can find where we have vertical tangent lines. So this would be where the numerator is non-zero and the denominator is 0. So we want to look at cosine of theta, that's f prime of theta, times cosine of theta, minus f of theta, so 1 plus sine of theta, times sine of theta. And we want to see when that is equal to 0. So we have cosine squared of theta minus sine of theta minus sine squared of theta equals 0. Cosine squared is 1 minus sine squared, so we have 1 minus sine squared of theta minus sine of theta minus sine squared of theta equals 0. So we have 2 sine squared of theta minus sine of theta plus 1. Yeah, let's multiply through by a negative sign, so we get a positive. 2 sine squared of theta plus sine of theta minus 1 equals 0. Now we want to factor that, so we get 2 sine of theta minus 1 times sine of theta plus 1 is equal to 0. So we're looking for places where 2 sine of theta minus 1 equals 0, or sine of theta plus 1 equals 0. So that means for over here we want sine of theta equal to 1/2, which is again when theta is equal to pi over 6 plus 2k pi, or when theta is equal to 5 pi over 6 plus 2k pi. So this is kind of the opposite of before. Before we were looking at where sine was negative a half. So now we have sine is positive a half. And then we also have where sine of theta is equal to negative 1. But we know that sine of theta is equal to negative 1 when theta is equal to negative pi over 2 plus 2k plus 2 pi k. Now notice, though, that now we're saying that the bottom of our derivative is equal to 0 and negative pi over 2 plus 2 pi k. And remember that the top we already looked at was equal to 0 when theta was equal to pi over 2 plus pi k. So notice that there's a conflict here. Not for every value. If we're looking at just pi over 2, for example, we're good. The top is 0, the bottom is not. But if we look at negative pi over 2, or 3 pi over 2, then both the top and the bottom are 0. So how are we going to determine what's going on? If we look at our picture, first of all, let's see if this makes sense. We have said that this is going to be at pi over 6. Yeah, that looks about right. And at 5 pi over 6, that looks about right. But then we're also looking at negative pi over 2, and that does not look like a vertical tangent line. Maybe right here. That could be a vertical tangent line. So how can we tell the difference algebraically? But can we show that? Well, let's pick one of these points where there's a conflict, and let's take the limit as we go to that point. So let's look at, in particular, as if theta is 3 pi over 2. We can take the limit as theta goes to 3 pi over 2 of our derivative. We know that it's 0 over 0 format, so let's do L'Hopital's rule. And we do L'Hopital's rule, we get this ugly looking expression. We simplify it a little bit. And now let's look and see what happens. We have 2 sine squared. That's going to go to, at 3 pi over 2, sine is negative 1. So that's going to go to negative 2. We have 2 cosine squared. At 3 pi over 2 cosine is 0, so that one goes away. We have sine of theta, and that one's going to go to negative 1 at 3 pi over 2. So we're looking at negative 2 plus 0 minus 1. This is what it goes to on the top. But on the bottom, the cosine of theta goes to 0. And notice how we factored that out. So it's multiplied by sine of theta plus 1. So this is going to be 0 times negative 4. Sine of theta is negative 1 plus 1. So the bottom here is 0. The top is not. Let's see, this is going to be negative 3 over 0 is what our limit is approaching. So that means we have a vertical asymptote. Now, how do we find area bound by a polar curve? Let's say we have a polar curve here, and this curve is r equals f of theta, and we want to find the area bound by this polar curve between theta equals alpha and theta equals beta. So these are 2 angles. Here's alpha, here's beta. And so we want to find this purple shaded region. How would we do that? Well, what we want to do is split this up into small pieces, just like we did when we were trying to find area with rectangular coordinates. But since this isn't rectangular, the way we're going to split it up is we're going to draw theta lines. So drawing in theta lines makes these little rays. And each piece then, as we slice it up, kind of looks like a little triangle or a little arc is how we're actually going to estimate it. So like if we look at this piece right here, there's a little arc of a circle. So imagine the whole circle that goes around the origin, where this little arc right here is just a little piece of it. Well, do you know how to find the area of an arc of a circle? So how do we find an area of one of these little wedges? It looks like a little piece of pie. It's a little part of a circle. Well, to find the area of a part of a circle, we know this from before. You use 1/2 radius squared times the change in theta. That's we're talking about now here. This angle right here, which is this bigger angle minus this littler angle. So that is giving us the area of a sector of a circle. So if we call our little wedge here W, one little wedge would have area 1/2 r squared change in theta. Remember, r is f of theta, so one little wedge would have area 1/2 f of theta squared change in theta. But then if we add all those up, we would get our actual area being the integral of 1/2 f of theta squared d theta. And we want to start making our little slices when theta is equal to alpha and stop when we get all the way over here and theta is equal to beta. So there's a summary of what we just said. We have the important conditions here where we have f being continuous and f being positive because we had a negative radius that would kind of mess this up. All right, so let's do an example. Find the area inside r equals a. Well, r equals a is just a circle of radius a, so we know what the answer ought to be, right? This is a circle. We know how to find the area of a circle. It's pi r squared, so this should be pi a squared should be our answer. So let's see if we can do this with the formula we just came up with. All right, so using our formula, we would have that the area is equal to the integral from 0 to 2 pi of 1/2 our function f of theta squared, so that would just be a squared d theta. So integrating would give us 1/2 a squared theta, evaluated from 0 to 2 pi, which would be 1/2 a squared times 2 pi minus 0, which is pi a squared, which is exactly what we expected. Let's try a little more challenging one. Let's find the area inside r equals cosine of theta. So first of all, do you remember what r equals cosine of theta looks like? So here's the graph of r equals cosine of theta. Remember, it's a circle coming over here to the side. And the first question is, if we want to find the area of the circle, we want to find these little rays sticking out and where they hit the circle. What values of theta are we going to need to use? This is usually the hard part of integrating in polar. So we know when theta is equal to 0 that we're right here. And now as theta goes to pi over 4, we're up here. Pi over 3, pi over 2. When we get to pi over 2, we're right here. And we've gone halfway around the circle. And then remember, when we're between pi over 2 and pi, when we were graphing this function, we have negative radiuses. So we actually end up tracing out this part of the circle again, getting all the way back to -1 when theta is pi. So to get this whole circle, we only need to go from 0 less than or equal to theta less than or equal to pi. If we went all the way to 2 pi, we would get 2 copies of this circle. So we want to integrate from 0 to pi, except for, let's be careful, we said the function had to be positive, right? So maybe we want to go from 0 to pi over 2, and it will also be positive. Let's look at the graph of cosine, right? Where is it positive? It's positive from 0 to pi over 2 and back to negative pi over 2. So maybe we want to take this whole region, and that would give us the whole circle. Or we could be even cleverer and use symmetry here. So this area on top, that's certainly positive, right? And if we had 2 of those, we would have the whole thing. So we're going to do 2 times the integral from 0 to pi over 2 of 1/2 our function, so that's cosine of theta, squared d theta. So let's go through that one more time. First of all, we figured out we could go from 0 to pi to make the whole circle. But then we figured out that between pi over 2 and pi, our radius is negative, and we don't want to do that when we're integrating. So we decided to just go from 0 to pi over 2 and double it. All right, so this is our area for our circle. And I'll let you guys go ahead and integrate that. Consider the circle r equals 1/2 and the circle r equals cosine of theta. Let's set up an integral for each of the shaded regions given in the picture below. So this circle here, that's r equals 1/2, and this circle here is r equals cosine of theta. So this point here is -1/2, this is 1/2, and this is 1. So first let's look at R1. So this green region, R1, is only bounded by r equals 1/2. And it's just a quarter of the circle r equals 1/2. So this integral we can set up as just the integral from, we could do any quarter of a circle, but let's do the quarter of the circle we're looking at here. So this is pi over 2 to pi of 1/2 our function, which is 1/2 squared d theta. So that's R1. Now let's look at R2. All right, so this region, region 2, rays in this region have an outer function of r equals 1/2 and an inner function of r equals cosine. So our integral is going to be 1/2 1/2 squared minus cosine squared d theta. And then the interesting things are what is the values of theta. So we want to stop, I think it's pretty clear, at pi over 2, but where do we want to start? We want to start wherever this intersection point is. We need to find the intersection point between these two curves. So to do that, we want to look at where is cosine of theta equal to 1/2. Well, that is when theta is equal to pi over 3 plus other stuff. But this picture here, we can see we're in the first quadrant, so pi over 3 is the one that we want. So we want to go from pi over 3 to pi over 2 to find the area of region 2. All right, now let's look at region 3. Region 3 is also going from pi over 3 to pi over 2, but now instead of being between the circle, the half, and the cosine circle, we're just inside that cosine circle. So we just get 1/2 cosine of theta squared d theta. Now consider region 4 and region 5. Both of these regions lie between theta being 0 and theta being pi over 3. Region 4 is inside the 1/2 circle, and region 5 is between the cosine circle being the outside function and the 1/2 circle being the inside function. So let's set up these last two. See if we can squeeze it in here where you can still see part of the picture. So region 4 is the integral from 0 to pi over 3 of 1/2, and we only need that inside circle there, which is the 1/2 squared d theta, because that's the only one it's touching. And then region 5 is, as I just said, we're going from 0 to pi over 3 and 1/2, and the outside circle is cosine of theta squared minus the inside circle is 1/2 squared d theta. All right, now let's find the area inside r equals 1 plus cosine of theta and outside r equals 3 cosine of theta. First, we have to figure out what these look like. R equals 3 cosine of theta is a circle over here on its side that goes out to 3. R equals 1 plus cosine of theta is a little trickier. If we look at a graph in xy, we would get starting at 2, going down to 0, like this. So when theta is 0, we're at 2. The radius is going to keep decreasing until we get to pi, at which point we're going to be at 0. So we want to go all the way around, because we're always positive. We're going from here all the way around to pi. And then our radius stays positive and keeps going all the way around, but it's going to start increasing again. So it looks something like that. So if we want the area that's inside this heart shape and outside the circle, we're looking for this region. We're lucky that 1 plus cosine of theta always has a positive radius. 3 cosine of theta, if we look at that graph real quick, it looks like this with a height of 3. So it's going to be positive between 0 and pi over 2. So we want to focus in on this region right here, and we want to split it into two pieces right at this bright red line. So this first area over here that I'm going to color red, in that area we are between 0 and pi over 2, and our outside function is the heart and our inside function is the circle. So there we're looking at 0 to pi over 2 of 1/2. The outside function is the heart, if we draw a line through there. So that's 1 plus cosine of theta squared minus our inside function is the circle, so that's minus 3 cosine of theta squared d theta. And then we want to add to that this region over here. But this region, if we draw a ray, we're only touching the heart. So this is the integral from pi over 2 to pi of 1/2 1 plus cosine of theta squared d theta. Now remember, even adding those two together, that only gives us half of the area we're looking for. So we take this whole thing and we're going to multiply it by 2. And that'll give us the area we're looking for. Let's look at one more example. we have r equals 1 plus 2 cosine of theta. We want to find the area inside the outer loop but outside the inner loop. So that already tells us it's going to have loops in it. But maybe let's draw this in Cartesian, figure out what it looks like. So we have 1 plus 2 cosine of theta. So we're centered around the line 1 here, but we're going up to 2. So we start at 3, we go down below, go all the way up, and you can see that's how we're going to get this loop here, because right here it goes negative. So if we draw it in polar, we're starting out here at 3, we're coming around, and at some point, at some angle, we're going to become negative and get a loop. So it's going to look something like this. And we want to find this area. Now, my drawing is not really great here, but this is the origin. So the first question becomes, for what angles does this inner loop start? We want to find the places then where 1 plus 2 cosine of theta is equal to 0. 2 cosine of theta is equal to negative 1, so cosine of theta is equal to negative a half. And that happens when theta is equal to 2 pi over 3 and 4 pi over 3 and other stuff, multiples plus 2k pi's. So what we're thinking here on this graph is that this is probably 2 pi over 3, and this right here is 4 pi over 3, or over here this is 2 pi over 3, and this is 4 pi over 3. And that makes sense because remember this one is pi, and this one over here is pi over 2, and 3 pi over 2. Okay, so how does that help us set up our integral? Well, we want to find just the inside between these two loops, but what's going on here that's weird is that this outer loop is not happening for the same values of theta that the inner loop is happening. So what I suggest we do is we find the whole outer loop, and then we find the area in the inner loop and subtract. All right, so how do we do that? The whole outer loop is going to be, well, let's just do this part up here, and we'll multiply it by 2. So that would be what? That would be the integral from 0 to 2 pi over 3, here's 0, of 1/2 my function, so that's 1 plus 2 cosine of theta, squared d theta. All right, so that's giving me just this top region. Then I'm going to multiply that by 2. That gives me, I guess I should have colored it like this. This gives me this top region. Multiply it by 2 gives me this whole red area now. But I just want the yellow area, so now I need to subtract the area of the little loop. How am I going to do that? This little loop is made when theta is between 2 pi over 3 and 4 pi over 3. So we could think we have our function there. So is that the area of the little loop? Well, it looks like it should be. If we do little radiating lines here and we just hit the function between those points, that's the area we want. The only problem is, remember that in this region, 1 plus 2 cosine of theta is actually negative. And we're not really allowed to do this for negative. But what if it were positive? If it were positive, you just end up with the same loop over here on this side. So actually the area is going to turn out to be the same. So in this case, we're actually finding this area and subtracting it off, but it's the same as this area, so it's okay.